Okay, so we were discussing M estimators and asymptotic properties of M estimator. And so to remind you, an M estimator is a solution of optimization problem like this, where we are assuming that we have IID samples from a base model. So we're forming these empirical averages of some function and some function of theta, in particular, if that function is log likelihood, then this would give you the maximum likelihood estimator. But there are other examples. So for example, there are quasi-likelihood functions that if you don't have like a proper model, you have something that looks like a likelihood, you can try to minimize that. You've seen, for example, that even if you don't have a likelihood, you can take the sample mean as an example, and get the sample mean minus this object or this function. So this M capital N is the notation for this empirical average, and this little m theta is just this basic function that goes into building this estimate. Okay, and so because we are under IID sampling, the idea was that we can use asymptotic results in probability, in particular law of large numbers, and asymptotic sort of this like results by asymptotic distribution, which is basically limit theorem. So there are two main limit theorems in classical probability. There's law of large numbers and there's the central limit theorem. And so we can use those to gain insights about the statistical performance. And in particular, the first question that we can ask is, if the data is generated from one of these distributions in the model, so for some theta naught, in the probability, in the parameter space, we're generating from T theta naught. So the assumption is that one of these probability distributions is the correct distribution. So we have a model that includes the true distribution, and then I'm maximizing. Well, actually, in this case, the theory is more general than that, even if the T theta naught is not inside the. So we have this family, right? So some of the things that they discuss are even more general. So you have this family. Hopefully, the theta naught is within this character space, but even if it's not, you can adapt these arguments. But for now, let's say there's a true theta naught in the parameter space, and you're generating data IID, and we would like to understand the asymptotic behavior of this. So as the sample size grows, the intuition is that if we have a good estimator, it should converge to the true parameter. Okay, and if this happens, let's say in probability, so convergence has to be specified because you're dealing with stochastic quantities. You're dealing with random variables, so this theta hat n is a random variable. For most of our analysis, or for most purposes, conversion probability is good enough. So what we want to basically is that the probability, let's say in the univariate case, scalar case, the probability that theta hat n minus theta naught in absolute value is bigger than epsilon goes to 0 for any epsilon. So what this means is that if I take a neighborhood, so this is basically, if you imagine, is a probabilistic version of the epsilon delta definition of the limit. Okay, so if you have the deterministic sort of statement, so a sequence converges to 0 if you ignore the probability. For some like large enough n, this is the indicator basically, if you want to place this with the indicator. The indicator is exactly 0. Okay, so this is the definition of indicator theta hat n minus theta naught bigger than epsilon. Sort of, you can say go to 0 or just 0 for large, for all n large enough. And so for every epsilon. And so we're replacing this, relaxing this, and we don't want exactly to be true. I want the probability to be smaller or go to zero. That's sort of a relaxation, probabilistic relaxation. And a lot of these properties of random variables that we discussed, you can think of them as probabilistic relaxations of deterministic ideas. Okay, so this is convergent probability, and so what we sort of did was to notice that this empirical average right around large number converges to a population limit or to a limit, and that limit would be the expectation of one of these terms. So these terms are IID for every theta, and so I'm taking the average of some random variables that are IID draws. So this could converge. This will converge in probability to the expectation of one of these. In particular, for example, like x1. So theta of x1 is like as a prototype of these random variables. If you take the expectation under the true parameter, now the law of all of these xi's are the true law. So this will converge to the expectation of this random variable under the true distribution, which is m theta naught, or sorry, expectation of theta naught and theta of x1. Okay. So we call this the capital M theta, and the hope is that because the functions are converging, these random functions are converging to this m theta, then maybe the argmax is also converging. And if the argmax of this happens to be theta naught, then I'm done, because say the maximizers of this are converging to the maximizer of that, and the maximizer of this, let's say, is the true parameter. So I have managed to prove something like that. Okay. The difficulty, however, is what? What is the difficulty in this type of argument? You recall? When you just right. So law of large number only gives you that this convergence holds for every theta. So fixed theta, this as a sequence of random variable converges to that as a random variable. So this means pointwise convergence of functions in the language of analysis. Okay. So convergence pointwise in probability is what we get, which is not enough for convergence of maximizer or even maxima. So we need a stronger notion. And so this stronger notion is somewhere actually between this and this uniform convergence, but uniform convergence is enough. So uniform convergence means if I look at the deviation, the worst case deviation or the entire parameter space convergence we call it. Okay, so this uniform norm or infinity norm of a function is basically maximum or supremum over all the values of the absolute value. So this notation is very often used in analysis. Generally, the sup norm of a function is the maximum over the domain of fx. And so if I look at the sup norm of the deviation, if it just converges to zero, probably then we're done. Okay. We did a counter example that what will happen if this fails. So we have here pointwise convergence, but not uniform convergence, and you can see that the convergence of minimizers or maximizers fail. And so we ended up basically stating this result last time, which is fairly general and abstract. So it's saying, suppose we have a sequence of random functions. At this point, it doesn't even have to be of that particular empirical average form. So this sequence of random functions converges. And then, okay, so there is an m, which is a fixed function. So both are functions of theta. And I'll look at the maximizers of this m and theta over the parameter space. And if this sequence functions converges uniformly in probability. So this is uniform convergence. And if the second condition holds, it roughly says that m theta has a unique maximum at theta naught. Okay. Then theta hat n is consistent in the sense that theta hat n converges probably to theta naught. Okay. So this result, or this rule, is like a technical way of saying things are unique. So if you imagine for every epsilon, if I look at the maximum of the function outside of a ball of radius theta, so look at theta naught, with a ball of radius epsilon around it. What this is saying is that the value of the function at the center at theta naught, this one, is strictly bigger than the maximum over this region outside the ball. Okay, and this happens for every epsilon. So it's slightly stronger than maximizers being unique. So theta naught is the maximum because the value function at this center is bigger than outside. Okay. This like prevents that in the case where things are compact, so the parameter space is compact is exactly equivalent to theta naught being the unique maximum. In the case where the parameter space is infinite, things could happen at the infinity. So this is preventing that, like that you have asymptotically an asymptotic maximum at infinity, which is not attained, but so the function sort of is maximum here and goes back up and like approaches the maximum outside. So this prevents this from happening, okay, at infinity. But if things are compact, you can argue the result. If this function is continuous and the parameter is compact, this condition is equivalent to theta naught being the unique maximum. So this then, in that sense, it's saying that this maximizer, so basically any maximizer, so this argument could have, you can have multiple, but pick any one of them and it would converge to theta naught. Okay. So it happens that theta naught is your true parameter, then you're good. Okay, so this is a very general result. Okay, so you have to design this and theta such that the limit, because theta naught is the unique maximizer, and then you're going to be consistent. Is that good enough? Questions? So originally I planned to prove these results, but I've decided to like try something else. I want to go quickly over all the results first because you want to do your homework problems. I want to give you a head start and to see these in action, and then we'll come back and prove these technical results. Okay, that might be better so that we can by the end of this week just cover everything. And then there's some very technical. So there are like 3 results. This is one of them. The other one is the asymptotic normality of estimators, and the other one is the delta method, which is simpler. So these 3 results we're going to come back and prove hopefully later. Okay, but this is the idea. So we need this uniform convergence. We need this of the maximizer, basically theta naught being unique or separation of the maximizer. So this is where things are not separated. So this maximum and like a potentially something at infinity are both like maxima. So there's a key step going on in this proof, which will come back. But there are sufficient conditions for this uniform convergence to happen. And we're gonna just state them and you can check. It's not hard to argue. Theorem 9.2, for example, gives you these sets of conditions for that uniform convergence. So if the parameter space is compact, oftentimes things are simple. So parameter space is compact. Those functions in theta x are continuous in theta. And then you have this basically moment condition. So the supremum of these functions, so the uniform norm of this function, for a fixed expectation. So the expectation is fine. This is like an integrability condition. Let's say, for example, these are bounded, it's definitely true. So under these conditions, that uniform convergence result holds for. So then we have Mn minus M infinity conversion probability to 0 for Mn that's constructed like this for this particular. But these are not the only conditions. So there's a whole industry in the statistics that try to prove these uniform results. So these are called in general, this kind of results for this type of thing is called uniform law of large numbers. So there are stronger versions of law of large numbers. And in particular, people would try to show something like this. Even more generally, I have a function class applied, let's say, to xi, minus the expectation of, let's say, one of them. I want to prove that the supremum over a function class converges in probability to 0. That's the general setting. So these are parametric functions. So you can see if my function looks like, my function class is the set of all functions that look like this. F that looks like that for theta in omega, that gives you this. But more generally, you can have a non-parametric function class, non-parametric. And then we generally want to show something like that. So these are called uniform law of large numbers, and the area of a statistic in which these are discussed in general is called empirical process theory. Which at some point, maybe in a more advanced course, you would see it. So maybe in 200C, you sequences of this. Or maybe if you were to attend a PhD program, maybe 15 years ago, you would see this. Okay. The more theoretical department, you would have like an entire course taught on this. There are books like maybe in the 90s and even like 80s, 90s, and early 2000. There's a huge like literature. If you're still interested in theoretical analysis, one of the more beautiful areas of theoretical statistics. And the idea is that generally speaking, the complexity of this function class like this determines whether this holds or not. Okay. So if the function class is very large, then this could fail. If the function class, for a function class that contains only one function, this definitely holds by the law of large numbers as long as this is integral. For two classes, for two functions, two classes, it will hold. For a function class with a finite number of elements, it will hold by the union bound, which you may see maybe. Many people know what the union bound is. Okay, so by union bound, it follows from the law of large numbers. But for an infinite class, you run into trouble. When things are compact, you can reduce it to the finite case, basically. But the general idea is that you want to reduce it to a finite subset. You want to approximate all the functions within the class by a finite set of points, or those finite set as false, and then there are the risk errors that control. But because it's a huge area, I'm not going to go into, but just know that these keywords, empirical process theory, uniform law of large numbers, if you search, you can just get started on reading, and it's a great sort of area to get yourself familiar with. There's some of the books on the web page. I think the Infinite Dimensional Statistical Models by Nicole and Ginée. That book has like an entire chapter that goes over these results. Okay, so let's take care of one argument. The other one is rather simple. That condition for the, let's say, soup over theta minus, I'm going to write it in this fashion, m theta being less than m theta naught. This one you can easily argue for yourself. that if omega, for example, is compact and is continuous and M has a unique maximizer, then this should hold. Okay. Just because the supremum is achieved, and I'm doing the argument on the next slide, which I'll let you do it quickly. But under compactness and continuity, basically, these would hold. And a bit of moment condition. Okay, sort of good. So, yeah, the key factor, the key takeaway is that the size of the parameter space matters for uniform convergence. So let's see an example. For example, what happens in the case of the maximum likelihood? Again, in the case of maximum likelihood, we have this is log p theta of x, right? And assuming that we are under the setting where the uniform convergence hold, that quantity, the m theta, so let's see what this guy is. So this is expectation theta naught of m1 of x, which in this case, I'm sorry, m theta of x1, which turns out to be expectation under theta naught of log p theta of x1, okay? And this is related to what is known as the KL divergence. In particular, it's easier for analysis purposes to redefine this m theta to be log p theta of x divided by p theta naught of x. So I can't, so let's say mn is 1 over n, summation I from 1 to n, m theta of xi, and then I write the MLE as argmax of mn theta. So I can't implement this in practice because I don't know theta naught. But the argmax would be the same as the MLE. So the argmax is the same if I drop this, because this will be the constant. So if you just plug it in, so the log theta x minus log theta naught of x. So we get the summation of the log theta of x minus the term which doesn't depend on theta. So the argument is the same. So for theoretical purposes, you can redefine and theta like that. So then if this converges uniformly to m theta, in which case this would be expectation under theta naught of log p theta of x1 divided by p theta naught of x1. So this quantity is really what's called the KL divergence. So this it can be written as integral p theta naught of x log p theta of x divided by, or let me write it, yeah. So we have to integrate this against the density at p theta naught. So p theta naught of x log p theta of x p theta naught of x, let's say dx or d mu x if you want. These are the things with respect to the wave measure. So this is really what is the negative of, okay, we redo this as well. So I can flip the two sides, p theta naught of x divided by p theta of x dx. And so this is going to be negative d p theta naught p theta, I believe. Yes, okay. So we're converging to this quantity. That's the limiting function, okay. How many people know the KL divergence? Okay, so this is the KL divergence between the density theta and the true density, okay. And one of the properties of KL divergence is that it's 0 if and only if the densities match. Okay, so this is going to be less than or equal to 0, and 0 if and only if theta is equal to theta naught. Okay, and so actually this is not true. This is not true. 0 if and only if p theta naught is equal to p theta as densities. We say almost everywhere. Whether p theta naught is equal to theta, so this statement, there's a caveat here, but this is true. So this is going to be 0 if and only if, so non-zero if it, like, okay, 0 if and only if this holds. So if this doesn't hold, then this would be strict. And so then if it happens that this is equivalent to this, so one side is clear. So if theta naught is equal to theta, then this holds. But this side we're not really sure. This side is true. But this side is true. I want the other way. Okay, so definitely this is always true. So if theta is equal to theta naught, then p theta naught is equal to p theta. But the other way may not be true. Anyone knows when, like, what is the issue in the other direction? Something that happened in your homework 1 towards the end. What was that? Yes, yeah, okay, so that's the keyword. So what is the connection of identifiability with this business? Okay, good, yeah, so the model, if the model is not identifiable, then I can have two different data that give me the same distribution. So I can go up to this, but I can't include that. So this part requires identifiability, which is good, identifiability. Because if you conclude that you converse it through parameter and the model is not identifiable, there's something wrong. Because it's not possible to identify where to converge. And this sort of clearly shows that, so if the model is identifiable, these two are equivalent, then this is strictly less than 0 unless theta is equal to theta naught. So theta naught would be the unique minimizer. Okay. And let's say if the parameter space is compact, then that condition is satisfied and then you're done. If not, then you have to verify that nothing happens at the infinity, which usually doesn't happen, and so it's still be fine. Okay. So there is this piece of identifiability issue that you have to worry a little bit about. Okay. But it's good to remember that basically consistency of the MLE is sort of a byproduct of the fact that the KL divergence has this property of 0 and only if the densities are the same. So this is a limiting behavior of the loss function, basically, or the you want the risk in the MSE case. Okay. So if your model is identifiable and if your regularity assumptions hold, which we didn't go too much into, but basically if the parameter space is compact and things are continuous, then you'll be fine. Then you get this, but this step is important. Good. So MLEs would be consistent under the regularity assumptions that we hopefully have. There are cases where they're not consistent in your homework problem, we will see. And so some of these would fail. Okay. Questions? Yes. Where did you first introduce theta naught? So the theta naught, the idea is that we are working under this model. Okay, so this is the working model, the IA, right? And then I just introduced it here into the definition of M theta for the theoretical purposes. Okay, so there is this true density. So this distribution has this density, and we are maximizing the log likelihood. The log likelihood would be up to constant equal to this. The constant being that. So this is equal to 1 over n summation I from 1 to n log p theta of x plus constant. That constant being negative log. This guy is negative 1 over log p theta naught of xi, which is not of concern because we maximize the volatility. Again, the way that you write it allows you to conclude that it converges to this quantity of interest. Even if you didn't, you could still argue this is easier, but you could, even if you didn't do this division, you get something like that without you take a naught, and it would have a maximum. The maximum wouldn't be like 0, it would be the negative log integral, whatever this leftover is. But this is cleaner. Sounds good? Okay. Any other question? Okay, so to quickly go over the other results to see where we can go with this. Once we have consistency, the next step is to control or like quantify the error, how far away from the true parameter we are. And so if you go back to the basic probability, if I have an IID sequence x1 up to xn with mean mu and covariance matrix sigma, so this is my notation for covariance matrix. You can think of it as the univariate case for now, if it's easier, just the variance. But I'm implicitly assuming these are random vectors. So all the things would work for vectors. So weak law of large numbers tells you that the sample mean, okay, sample mean here is 1 over n summation I from 1 to n xi. The sample mean is consistent for the population. That the same law of large numbers, you want to translate it to language of a statistic, is saying sample mean is consistent for the population mean without much assumption in the problem model. So you don't have this parametric model. Whatever the true distribution is, it has a mean, and that will be consistent with the mean because you can really follow the mean. And so, what is the CLT? CLT, if you write it as a statistician would write, it would be this statement. Okay, so if I look at the deviation of sample mean minus the limit of the population mean, and rescale it will be n, this no longer goes to 0, but it stabilizes in the limit, and the limit will have the distribution of P0 and covariance sigma, or covariance matrix sigma. So that's the statement of multivariate CLT if you want, restated in language of statistics. Oftentimes they write it in probability for the sums of random variables. The statisticians would write it for averages, okay, means. So what CLT does, if you look at this carefully, is characterizing the fluctuations around the limit. Okay, it's saying that, okay, this goes to the 0, but if I really scale it by proper scaling, if I multiply by each n, then it no longer goes to 0 or to infinity. It just stabilizes. Stabilizes, so there's kind of like a distribution. It's not going to be converging to a particular value, but it will be fluctuating like normal. Okay. And so that's the notion of convergent distribution, which I'm hoping that people understand or have seen before. So many people have seen. Okay, we're going to review a little bit some of the properties. But the idea is this is a different mode of convergence. This is not like convergent probability. It's weaker than convergent probability. The idea, for example, is roughly that the distribution converges. So the distribution of this converges in the sense that the probability that this belongs to a particular set converges to the probability that the normal distribution belongs to that set for sufficiently regular sets. regular sets S. So in particular, for the normal case, I believe for every like measurable, for L measurable, we do. The set S depends, like the sets at which we convert would depend on the limiting distribution. So if it has point masses and stuff, then you have to worry a little bit. But for normal, things are fine. Okay, so that's convergence distribution. We want to, so this is giving you an interesting fact about this estimator. So if you want to say it in the language of statistics, you would say sample mean is asymptotically normal. Okay, and with this distribution. And then you can use this distribution to for example, confidence intervals. Or do other comparisons. Because I know, for example, what the probability is. This belongs to a set that converges to a control. It's a final set. If the probability converges to 0.95, then I have a set that contains the I can rearrange the rule. You can rearrange. You get a set that contains two parameters, the high probability as a type. Okay, so that's the primary. One of the like primary uses of these, that's in first order, or if you want second order asymptotic arguments, let's call this first. Zeroth order would be consistency. First order is this asymptotic normality. So we want to prove results like this for our general estimator. So suppose I have theta at n converges in probability to theta naught. That's the first step. Then I'm going to say maybe I can rescale this. Let's say by a proper scale, maybe we can, which happens to be the case most often. And then this converges in distribution to something, which is often normal. If you have like a normal distribution, then that would be great. Otherwise, I would like to have like some sequence of numbers can like multiplied by this converges to in distribution to some stable distribution, some distribution. That's the goal. Okay. The next step. Does that sound good? Questions? Okay, in order to do this, we're going to use some properties of convergent probability and distribution because it gives us a calculus that we can use to manipulate these statements. We want to like extract this type of information from basically CLT. So we need to be able to manipulate these convergent statements. And this basically summarizes the basic things that you should know. We're not going to prove it in this course, but if you're interested, you can look up in reading of the advanced book, for example, the Van der Waals asymptotic statistics, maybe in the first chapter, first few pages. So the first thing is convergent probability by convergent distribution, but not vice versa. Okay. So if a sequence of random variables converges to some random variable x, then in probability that it converges in distribution to that random variable. However, you should note that the meaning of this is different. So this is saying that the law or the distribution of x converges to the distribution of x. Nothing realistically converging. That means in reality, like these could live in different spaces. This would be like, you can say that the x convergence is the law of x. For example, this is normal. I said converges in distribution to normal. So, but in any case, so this is true. So if x converges probability to x, then has to converge in distribution to x. The reverse direction is not true. So this shows that convergence probability is stronger than convergence distribution. However, if the limit is a constant, then they're equivalent. So when you converge it into the constant in probability, it's equivalent to converging it to it. The next result is continuous mapping. So x converges to x in any reasonable mode. Probability distribution, or let's say almost sure which we don't really use, but let's say probability or distribution. And then it's continuous, then f of x converges to f of x in the same mode. So for example, if this is probability, then this would be probability. If this is distribution, then it would be distribution. So basically, these convergences are preserved under the continuous mapping. For that reason, it's called continuous mapping theorem, continuous mapping lemma. The next one is really tricky and very interesting. It's saying that if x and conversion is solution to x, a random variable, and if y and conversion is solution to c, constant, then jointly they converge in distribution. So x and y and as a vector, or whatever, but still converges to the vector x and c with distribution. This is very useful, and it is not true if both of them, the limits are random. So you need one of them to be constant. So this is often called the Slutsky's lemma, or the consequences of it that we'll see are called Slutsky's lemma, but this is the base result. So if you combine this, for example, combine this result with continuous mapping theorem, you get very interesting statements. So if xn converges to x in distribution, for example, and yn converges to c in distribution, then I can apply this function f of, let's say, x and y is x plus y. Okay, because by a Slutsky we know that x and yn converges in distribution to xn in c. Then by continuous mapping theorem via this function, I get that f of xn and yn converges in distribution to f of xn and c, which is equivalent to saying that xn plus yn converges in distribution to x plus c. Sorry, this is x. The limit doesn't have any n in it. Okay, so this is the result. So basically, xn plus yn, so xn converges to x, yn converges to c, and then sum converges to this sum. This is an application of that result combined with continuous mapping on R2. Because the summation, this is continuous mapping from R2 to R. Continuous. Okay. You can also do it with x times y. For example, you get that xn times yn converges to c times x. Okay. You can also do it with division, but you have to be careful because let's say x over y is only continuous where y is not zero. So if limit c is non-zero, then f will be continuous on the appropriate domain, and so then you have xn divided by y converges to x over c. I'm going to state the result in the next slide more formally. Is that clear? This is a very useful result. Oftentimes these consequences are called the Slutsky's lemma. So you see people supply Slutsky's result. So you have something like that. And this allows me to like basically replace things with their limits. Xn plus yn, or just replace x with the limit, this limit, and I'm be happy. Sounds good. So we'll see this in action. The next one is xn converges to x in probability, yn converges to y in probability, the jointly they converge in probability. So in the second, like E compared to D, I don't need one of them to be the limits to be constant. So both can be random. So this again shows the fact that the conversion probability is stronger in conversion distribution, because this always implies that. But we'll see an example that this wireless basically two not constant, but both of the limits are random. So compare D and E, you'll see the difference. And finally, in xn conversion distribution to x, and you have another sequence yn whose distance with x converges to 0, then yn is going to converge to x in distribution as well. So this distance has to converge in probability to zero or in distribution. Because convergence to a constant is equivalent. So because the convergence distribution to zero or in probability to zero. But this distance is like in scalar case is just saying xn minus yn converges in probability to zero. Okay, so I have a sequence in distance to another sequence converging probability to zero, and that sequence converges distribution further, and my other sequence converges to the distribution to the left. Sounds good. D is like a distance. So for example, in R, d of x and y is the absolute value in R. In Rn or Rd, it could be, for example, the norm, or any metric would like. So yeah, so the metric that goes into the definition of convergence probability, basically. So there is like generalized version of convergence probability, right? So when you say convergence probability, the probability of the distance to, let's say, this is really, okay, so I'll go back up. Where do we define? Yeah, so this is with this, for example, definition of convergence probability. And then you have to worry a little bit about if you're dealing with a metric space, general metric space. Actually, this is fine, I think. As long as you're dealing with parameters, it's fine. But for us, we're not going to worry about general parameter space. We're gonna work with Euclidean parameter space. But these statements generally hold in more fancy mechanisms. You just have to be able to like set up the probability space correctly, which is out of the scope of this course. Okay. So you need like a metric measure space. So that problematic and stuff. But if you can put a probability distribution in the space, or like random variables basically taking values in the metric space, if you make sense of that, then things are fine. Okay. We're not going to worry too much. That's a good question. No. There are different ways that you can like generalize convergence distribution. The easiest way to generalize is anyone knows like how people define convergence distribution, more general metric spaces or more. Also, you want to also consider that you make Pn of A for A is a sigma. Pn of A equals convergence to P of A for all A. Yeah, so okay, so that's one way of doing it. So you can say, okay, so I can say probability. So xn converges to x in distribution if probability that this belongs to A converges to probability that x in A for like a sufficiently general class of A. It may not hold for all like A in the sigma algebra that you start with, but it depends on like the regularity of this. So open, like close. So this is tricky. Depends on what the limiting object, the solution of the limiting object is, but you can check. So there are some features at the boundary. So for open sets, for example, when you okay, the set is for closed versus open versus half open, closed, things at the boundary would be tricky. So for example, if you in R, if this thing happens in R, this limit has to hold at any continuous point of the limit. If the distribution has a distorted discontinuity, then you don't have using this as a discontinuity of the limit. Okay, so if you have a, so this, for example, in R, this is equivalent to just requiring that this belongs to negative infinity and x, because from this I can construct any other reasonable, measurable, Borel measurable. So you just, sorry. In R, this is equivalent to just requiring the convergence of CDF. But you don't need convergence to get points X, which are in latency ranges is continuous. So it only needs to hold for all X in like a set of continuity points. X at which the limiting CDF is continuous. But for the normal run, this is the normal run, and then it's continuous everywhere, so it holds for all X. But if it's not, then you just have to verify this holds for all X except at that discontinuity. So there are technical issues you have to worry a little bit about if you want to go that way. The more general thing is which I like better, is I'm just going to mention and move on because of time. Sorry. The other way is to say that expectation of a function of xn converges to expectation of f of x for all f bounded and continuous. Okay, so f maps from whatever the space you are to R. Okay, as long as this holds for all bounded continuous functions, then converges well. But conversion is solution. So then this is oftentimes taken as the definition of convergence in distribution. So you can basically, this idea is very powerful. You can like, instead of looking at measure, you can see what they do to functions. So how they operate their functions, see how they integrate functions. And so as I vary the functions over a large function class, I just we can sort of characterize the measures. So two measures are going to be the same. For example, if you have if this holds for all f, let's say CB, okay. I'm going to write it like that: continuous and bounded functions from X to R. So for all f in continuous bounded from X to R, if this holds, then the two distributions are the same. Then X has to have the same distribution as Y. So if you're integrating a lot of functions and the results are the same, then the two distributions, the two measures have to be the same. So this is basically the limit. So this extends very well to general cases, because as long as in a space you can define continuous functions, which you can do in matrix spaces, continuous and bounded functions, and so this is easy to generalize. Okay, and then like another point is, this is very powerful because it can also measure the distance of distribution. So again, for example, now that you know like the uniform idea, so I can like, for example, measure how close they are actually by looking at this difference, supremum over the function class, continuous and bounded. Okay, so this defines a metric actually between distribution. It's close to 0 and you're fine, but it can also characterize how close they are. Okay. So the deviations of these expectations over these test functions. And I can later replace this with other function classes that did different metrics on the space of quality measures. So change this. And so this you can think of it as some sort of a distance between the distribution of xn and the distribution of x. We get different metrics. Which could be like a whole different course. But so this is side note. Okay. Doesn't concern us, but just So this idea sort of can be explored and leads to other interesting stuff beyond convergence. The convergence distribution. Okay, sorry. Okay, so back to this. Any questions about? Okay, so maybe move on to this. This is the statement that I mentioned about Slutsky. So, for example, if xn convergence solution X, y convergence solution C, and here you can do scalars, they can be vectors, they can be matrices, they are you can use them as vectors and vectors, and so they're all natural in the space. So if this holds, then xn plus y into x plus c. This will hold, and these will be matrices, but that's fine. So if x and y are compatible, so you can throw these matrix multiplication, and c times x also be valid. Y and inverse times xn, or c inverse times x, everything could be like a matrix or scalar. The last I'm assuming you're going to see is like convertible or non-zero in the case of scalar. More generally, incontinuous functions converge. And so this is oftentimes the statement of the Slutsky's lemma. Okay. We'll see an example shortly. Just one point is whenever you have xn converging to 0 in probability, this is written as xn is little op of 1. Okay, if you know the op, the O notation, big O, little o, in analysis, the sequence of convergence to 0, they say is O of 1, little O of 1. And so this is convenient for us. If you convert the problem to 0, you say O of Q of 1, little O. Okay. And then you can use O calculus to write some of these statements rather simply. So for example, if xn converges in probability, so this is by definition. So if xn converges in probability to 0 and yn converges in probability to 0, then by a Slutsky, I have that xn plus yn converges in probability to 0. Okay, so if I want to write this statement in O notation, I would say I have a term xn which is op of 1. I add it to a term which is op of 1. The result is op of 1. Okay. Adding two terms that are op of 1 produces op of 1. The same. Adding xn plus yn, each one is converted to 0. The result converges to 0. Okay. So this is like a compact way of writing, and it's very convenient in manipulations. Right, so you have like a large term, you don't want to like call it something and say, okay, this goes to 0 and then the other goes to 0. Now I have the addition. So you just say, this is op of 1, this is op of 1. I have a summation, it's going to be op of 1, just ignore it. Good? Yeah.
So isn't Slutsky saying convergence in distribution?
Yes, so it's convergence distribution.
So we were showing you using Slutsky thing.
Oh. So, okay, is this okay or constant? Constant. So it's constant. So this is equivalent to C. So this is equivalent to D, right? Because of this fact. Okay. Yes, good point. Yeah, so if both of the limits are constant, then you can just upgrade everything to probability. There's no upgrade really. Okay, so in the remaining time, I'm going to do a counterexample and an example of application of these, and hopefully next time we can talk about asymptotic normality. So this one, we really want to do actually. Let me come back to the maybe counterexample, come back later, see if we have time. So that slide gives you a counterexample of what happens when you have convergence to something on random, and this is all things. So it's not particularly important, so let's skip this. If we have time, we'll come back, but you're welcome to read this. Let's do the example. So I want to use these properties to prove some sort of asymptotic normality results from basic CLD. So I have a sequence of IID observations, expectation mean, variance, sequence squared, sample mean, we know is consistent for mu, so I know that xn converges in probability to mu, which we know also is equivalent to saying xn converges in distribution to mu. So this is by the law of large numbers. And I also, for example, know that by the CLT, root n xn minus mu converges in distribution to normal with mean zero and variance sigma squared. Okay. Now we have this sample variance, which is 1 over n summation I xi minus x bar squared. So if you want, this is x bar n. Right. And so I from 1 to n. Sometimes you write it as 1 over n minus 1, but we're worrying about asymptotics, it doesn't matter which way you go. So let's do that. So I have this sample variance. And the claim is what that I want to show is that xn minus mu divided by this sample standard deviation. So under this divided by mu, then now this conversion to the KDE to normal 0 and 1. So if you have seen these problems like this, statistic, this is t statistic. Like, this is minus 1 is perfectly t statistic, but approximately t is statistic. And so what this is saying is that t statistic conversion is solution to a normal when n is large. So this is the distribution theory result because we're not assuming that x has a normal, so you come from a normal distribution. The final sample analysis would show that if they're coming from a normal distribution, this has a t solution with n minus 1 degrees of freedom. Assuming that n minus 1 here. But in the same, even that we converge to normal 0. The t as n was large converges to normal, but even without something, so whatever the solution xi are, and then n is large, it's approximately normal. So then you can use this to build confidence intervals. For the mean, if n is large without assuming anything about the distribution. Okay. So let's see, is the statement sort of clear? So let's try to show you how we can do this using just these basic properties that we discussed. So I know these facts. Okay, so these are from law of large numbers and CLT from basic probability. What I have is this Sn squared, which is 1 over n summation I from 1 to n, xi minus x bar n, which if you expand, this is an empirical variance, so it has the same decomposition. The first moment, the second moment squared minus the first moment squared, so that's expectation of xi squared minus expectation of x squared. So that's basically x bar n. So let's first see what this converges to, okay? So the guess is that this is converging to the variance in probability or distribution. So how can I show that this converges to, basically it's consistent for the variance. So xi's are IID, right? IID, and I just know from some distribution with mean mu and variance sigma squared. That's all I know. And so we know that x bar n is consistent for mean, depending on the consistent for sigma squared. How can I use those properties to argue? Yes.
The term on the right, is going to converge to mu squared because it's mu is happening there.
Which one? This one?
Yeah.
Okay, so good. So this one, x bar n squared converges to mu squared in, you can say distribution or probability doesn't matter. So by continuous mapping theorem, right? So x squared is like fx equal x squared with continuous function. So we dealt with this one. So how about the rest? What about this first term? What do we know about? Can I invoke some result? First argue what this converges to rigorously. It's an average. Law of large numbers. So assuming that, but implicitly we're assuming that these are finite because the variance exists. So this converges in probability to the expectation of x1 squared by the law of large numbers. Okay, which happens to be, as mentioned, sigma squared plus mu squared. Okay, so this is basic probability. Okay, so I know this converges to something, this converges to something. What can I conclude about that? The Slutsky. Using the Slutsky, this converges in probability slash distribution to something. This is to something. This is the difference. So the difference converges to the difference. So by Slutsky theorem, we know that this guy is going to converge in probability slash distribution to mu squared plus sigma squared minus mu squared. The limit of this minus the limit, which is sigma squared. Okay. So prove that this is Sn squared is convergent, or like say consistent for sigma squared. Okay, that's the statement of consistency. Saying Sn squared is probably to the desired quantity. You can see like these properties combined with law of large numbers allows you to prove consistency of Sn squared very easily. Okay. Can I conclude that Sn also converges to something? Yeah, so this converges to square root of sigma squared by, so let's say Sn is the square root of that, so converges to square root by the continuous mapping theorem. So Sn is consistent for standard deviation. Okay, now going back to this quantity, now I have, let's see, we can do xn minus mu divided by Sn. So now I want to handle this quantity. Okay, any idea how to deal with this? Scroll up. Is that good enough? Yes, but you have to maybe rewrite it to be a little more clear. Sn over n, why?
By that from x1 and
the numerator by CLT, so this I just rearranged. So the numerator we know by CLT converges to in distribution to normal 0 sigma squared. Okay. And the denominator is converging to right in probability or distribution. Okay. Can I now use the Slutsky? Yeah, so this convergent distribution to something is not constant, but this one is constant. So at least one of them is constant. So Slutsky apply. So be careful here. So this converges in distribution, no longer probability, right? Convergent distribution to basically, let's call this Z, random variable Z. Z divided by sigma distribution. Okay. And Z is divided by sigma has distribution normal 0, 1. So you converge to normal 0, 1. Okay. This is the tricky application. It's the one is in the convergent distribution, the other the sigma, and then we're applying basically this sort of idea in divide. Okay. So very simple application of these results allows you to prove the so-called dimension-free result. Sorry, distribution-free distribution free result, which is providing like asymptotic distribution for this quantity, basically without any assumption on distribution beyond the fact that the mean and the variance are mu and sigma squared, which is not saying not much. So basically that this is like has finite moments of the second order, like just under the assumption that the expectation of x1 squared is finite, then basically you have this result. So what is an application of this? Building a confidence interval, which we'll see, but let me do the example. So what we know, for example, is that the probability that this guy Sn over root 2, let's say the absolute value bigger than 1.96, this converges to probability that a normal 0, 1 is bigger than 1.96, let's say, which is roughly 0.95, something like that. Okay. So that if that's the case, then I can rearrange. I get that if you rearrange this, you get that mu belonging to x bar n minus 1.96 Sn divided by root n, and x bar 1.96 Sn divided by root n. The probability of this converges to 0.95. So this would be called an asymptotic confidence interval at this level. So it's a random set that contains the probability asymptotically the desired value. And so you can see the length is controlled by this standard deviation, and it's very similar to your t kind of statistic, but if you do it with t, you would these 1.96 would be something different based on the quantiles of the t. But here you put it for normal, and asymptotically it would be correct. Okay, it's asymptotically valid.
I think it might be less than.
Oh, yes, you're right. So this would be correct. This is less than, let's say less than or equal to 1.96, yes. Okay. But so you can see like they're useful. So if you manage to prove results like this for our estimator, then we can build confidence intervals for our estimate. So that's the plan for next time. Okay. Any questions? Yes. That's sort of none of these results will tell you that. Yes, that most likely depends on the distribution under consideration. So if things are normal, you're much better than if they're heavy tails. So that's where these distances to distribution matter. So there is also variability. Various inbound with the healthy hot scale for the general distribution. Which is like this is one of the root n. But then we get an error. I'll talk about that maybe next time. Just remind me. Yes. Thank you.